Welcome to Construction Tech, presented by House Accelerator, a catalyst of zero carbon building. We're happy you're here. We welcome all comers to our exploration of how to slash the greenhouse gas emissions of our buildings and make them more resilient to the extreme temperatures, wild weather, and grid insecurity caused by climate change. With our co-hosts, Kevin Brennan, Shannon Pendleton, Sean St. Amour, and Mark Willey, we produce this weekly series to dive into the details of Passive House construction practice, with a technical focus on technique and technology in the field. New to all of this, please visit the Passive House 101 section of our website to get started. With that, please enjoy Construction Tech and pose your questions in chat for the discussion session following the presentation. Thank you. All right, everyone, welcome to Construction Tech Tuesday and this special presentation with Chris Magwood. We're really looking forward to it, and we're happy you're here. So with that, co-host, please take it away.
Thanks, Zach. Thanks to everyone for coming tonight. I'm Shannon Pendleton, zooming in from New Hope, PA. And I'm excited for tonight because we have Chris Magwood here from Builders for Climate Action, among many other talents. So get ready to learn about carbon studies software and what it means to be a builder when you think about this. How about you, Mark? What are you looking forward to tonight?
I'm looking forward to everyone's comments and questions. My name is Mark Willey, and I'm with U.S. Engineered Wood, and really excited for tonight, especially because Chris presented 4 times earlier today. So the motion is going. He's chasing endurance. I'd like to roll out challenges. So there's a lot of familiar faces, and I'd like to wave and give thumbs up to each of you. And my challenge for tonight is, if there's a slide that really captivates you, take a screenshot of it, share it on social media, and tag someone. Make sure that that they know what you're watching, what you're interested in. Pass it forward. Speaking of pass it forward, who's next?
Thanks, Mark. I'm Sean St. Amour, and I'm happy to be here because I actually got to meet Chris Magwood when he gave a presentation at Trinity Western about 3 years ago. And I wasn't there, but I watched on YouTube, and I actually liked it so much, I actually made it my intro to all of my future presentations because I wanted people to learn about what he was talking about at the time was the carbon elephant in the room. Well, I'm glad that we have Chris Magwood in the room tonight.
And I am also looking forward to watching Chris. So this is going to be a lot of fun. Thanks for giving me a few minutes. We wrote an article about this about a few weeks back, but I also wanted to kind of more officially announce and also introduce John Knapp, who's here today, the fact that we are launching Source 2050. So and it's separate from the accelerator, although I'm sure there'll be some sort of combination at some point. But it's John Knapp's running it, and it's a multi-vendor marketplace site for all things passive. And very similar to what we were excited about doing with the accelerator, where we're trying to aggregate as much information as possible and let people learn from each other. I feel that the marketplace desperately needs a single source where everything can be found that you need, making the bar to entry much lower. So I know everyone has strong opinions of what something like that should look like. Some people might have things that they want on it. Some people might want to be the first people to try it out. We're going to put a link in the chat. So as we develop it over the next month or so, if anybody has any ideas, wants to be on it, wants to be included, feel free. We like that. So thanks
for that, Mike. I'm excited to see what 2050 comes into, how the marketplace works. And then I'm also excited about tonight's presentation. I had the great privilege about a month ago of presenting alongside Chris at an AIA presentation. How low can you go as far as the presentation to that group? And it was exciting, and seems like we have similar backgrounds. Chris seemed to be in favor of cellulose. I'm a cellulose contractor. I'm a trainer. I train people. Chris trains people. I'm interested to see what's happening here, and I've always been intrigued. And then next thing you know, I opened up a magazine, and Chris wrote an article in it. So he's all over the place. So I'm excited. I'll stop delaying you guys. Let's get on with the feature presentation. Chris.
Okay. Hi, everyone. This is like a spectacular array of faces. I have to scroll through screens of them to see everybody, but thanks so much for joining tonight. Yeah, thanks everybody for having me. I'm really excited to talk to this group. I love what is happening at Passive House Accelerator, and really excited to be able to bring this piece to what everybody's trying to do, which is figure out buildings and climate and what we do and how we go forward, and keep building amazing buildings for people who need them, and not wrecking the planet as we do that, and maybe even helping rescue it a little bit. So this presentation, I warned people who came on earlier, you're getting a bit of a Frankenstein presentation in that I've patched pieces of different presentations together. I feel like this group has a very specific, already established kind of knowledge base and some interests that are unique. So all the information is here. You'll just see the kind of format change maybe sometimes between slides, but hopefully everything is here in a logical order that you're able to follow, and looking forward to a discussion at the end too. So there's one of the bases for this presentation is this report that I just helped author with Builders for Climate Action and Natural Resources Canada, which is the branch of the Canadian federal government that's responsible for home energy efficiency and all the programs that the federal government offers there. And we did this study, achieving real net zero emission homes, and it was the first time that a national government has really, taken a dive into material emissions and trying to see what they mean for the country. And it's the beginning steps of trying to figure out how this might fit into the regulatory world. So I was really excited to be part of it. But you'll see partway through this, we also segue into a bit of a presentation. We've been helping the cities of Nelson and Castlegar, BC, also study this for their region. And they're actually going to be instituting some incentive programs. And so those two bits of work are kind of coming together in this presentation. So very brief background, because I think everybody knows the story by now, but all of us have been working super hard at figuring out how to eliminate or greatly reduce at least the operational emissions that come from buildings. Such an incredible focus over the last 20 years of, if we really think back, when I built my first house, my building inspector laughed at me for wanting to put more than R12 in my walls. He just thought that was the most ridiculous thing he'd ever heard. Why would anybody do that willingly? And so it's a long, we've come a long way from then till now. And, we've all done really great work to really address that side of the emissions puzzle. But what I've been looking at recently, and honestly, my own dive into this came from about 10 years ago. I wanted to know what the carbon footprint of the building that we were working on at the Endeavour Centre that year might be, out of kind of just interest, hey, what does this look like? And that started me down a sort of 10-year rabbit hole of trying to figure that out, mostly because when I first started, I couldn't figure it out because nobody seemed to know. And then my interest kind of happened at the time that a lot of people got interested. And so a really interesting kind of body of knowledge has grown in that past decade. But the specific thing that I want to talk about is sort of the material emissions, this red highlighted bit in a life cycle of a building and its materials. And the reason that I want to focus there is that product phase, or what people often call cradle to gate, is where the majority of the emissions from all the materials that we use in buildings happen to occur. Depends on the material, but somewhere between sort of 70 to 85% of the emissions that are going to happen over the entire life cycle of a product. So from its initial raw material harvesting to when it finally is taken out of the building and, you know, incinerated or landfilled or whatever happens to it at the end of its life, almost everything happens up front here. And so when we're thinking about addressing the climate, today's emissions matter a lot, and here's where most of them lie. And they, you know, this is where we can dive in and really address these. The other phases, in particular, transportation to the construction site and construction site emissions, tend to be sort of between 5–10% of the total life cycle. So not as big as most people think, but not insubstantial either. But you know, it's hard to address that broadly because where you are, where materials are coming from, how you're getting to the site, what kind of energy you're using on the site, all of those things are very particular and unique. Whereas the material emissions, you know, most of these things are built in factories, and it's very easy to you know, assess what's going on in that factory. And so we know that the emissions we're sort of recording and understanding here are quite rigorous and understandable. And so we get the data that sort of driving these studies from these documents called environmental product declarations, or EPDs. And that's an internationally standardized way of reporting on a bunch of different environmental impacts from, in this case, building materials, but the methodology is actually used for all kinds of products. So each product has a category that it falls into. So you don't necessarily use the same rules for, say, framing lumber as you do for flooring. So within each product category, there's a set of rules. But basically, an EPD makes sure that everybody's counting the same kinds of things in the same way according to the same methodology. So we get a pretty comparable look between products in the same category. And so I take the global warming potential that they report in an EPD and figure out what that means for the amount of material in a particular building. And first, for my own purposes, I started to build out a spreadsheet of all of these EPDs and wanting to model my own buildings and some research buildings I was doing. I kind of built a sort of half-assed spreadsheet that gave me the answer, but that if anybody else looked at it, they wouldn't have known what was going on. But that has been refined over time. We built a version of it for Natural Resources Canada, which they call the MCE squared tool. We also have a version of it called Beam. Both of them are going to be out in public before the end of this year. So excited to kind of have that tool get out into the public. And you probably can't see this on the screen, but essentially, you know, each tab on the spreadsheet is a different part of the building. This is a snapshot from the exterior walls, where you know, we've told the software how much wall area we have. We've given it an R value. And what I really like about how we built the tool out is that right away you see a comparison for the building you're working on of the carbon footprint of all the different materials. So I can look, you know, see, oh, fiberglass would give me this in this building, blown in fiberglass that, mineral wool this, cellulose that. So, you know, it's this really great sort of tool where you get to compare the actual results for your building right away. So you can sort of decide on making material decisions and material swaps here by seeing the carbon footprint in kind of real time. So that tool is behind this Enercan study that we just did. And the study looked at, we sort of, it's not based on real homes, it's based on archetypes. So Enercan has a bungalow, a 2-story, and a row house that they have plans for, that they kind of use as like the typical kind of single family homes in the country. They gave us Hot 2000 energy models for these archetypes at tiers 3, 4, and 5 of the National Building Code, 5 being sort of the most energy efficient. It's kind of like the net zero ready version of the code. And they gave us models for 5 cities across the country: Vancouver, Prince Albert, Saskatchewan, Toronto, Quebec City, and Halifax, Nova Scotia. And then we built up 4 material scenarios for each of those models. One where we kind of picked the highest carbon option in every material category. One where we picked pretty typical selections from the mid-range of the options that are available. One that we picked what's the best material, in other words, has the lowest carbon footprint, but it is widely available and code compliant across the country. And then a final model where we just picked the best option, whether it was, you know, a typical material or code approved or not, so that we could kind of, we're sort of bookending the study with a worst case and a best case scenario, and then showing a bit of what is possible in the middle. And so this part, you're all gonna get how this part works. So I'm looking at the 2-story house from Toronto here, but things mapped out pretty similarly across all of them. So tier 3 is kind of our building code norm right now. So it's kind of like a code compliant home built today, heated and the hot water done by gas. And that building from the Hot 2000 model has about 3.5 tons of emissions per year, or I just extended that over 20 years. So 70 tons over 20 years. And that's probably about what you would all expect from something in this climate. If we bump that house up to tier 4 and it's still on gas, it's great. We dropped, you know, 20 tons of emissions over those 20 years. It's down to 2.7 per year. So, you know, clearly moving buildings along the energy tiers does what you would expect it to do. The tier 3 model, if we change it to all electric, so an air source heat pump was doing the home heating and an electric resistance heater for the hot water tank. Even at tier 3, you know, the operational emissions have dropped to under a ton per year, 14 tons for the 20 years. So, you know, obviously you can see there's a big difference between using a fossil fuel and using relatively clean electricity here in Ontario. If we bump that house, that electric house along to tier 5, we've got it down to under 0.5 ton per year, just under 9 tons for the 20 years. So all of that is not news to you. You all know that that's kind of how things go. What we're trying to provide them in this study is what is this end number after 20 years if we add the materials to it, right? Because that's this operational side isn't the only carbon footprint that building is going to have. Its materials also have ones, and we don't know that answer until we know this answer. So in the study, this is what we found. If we pick the worst materials in their category, and these are not uncommon materials, this includes things like brick cladding, it includes things like XPS insulation under the slab and around the basement, you know, spray foam insulation in the walls, you know, not unusual materials. It's this model's maybe unusual in that we put them all in one building, but you can see what happens. The carbon footprint of just the materials absolutely dwarfs the operational emissions. So, you know, the vast majority of the emissions lie here. The material emissions for this one are equivalent to 315 years of operating emissions. So, you know, if we're going to make a difference in this building, we're going to make the difference in the materials and not anymore in the operations side. Here, you'll notice that the scale has changed a bit. I had to adjust it to fit that last model in, but our more moderate materials example is 31 tons of material emissions, taking the building to 40 tons over the 20 years. And so this is, you know, this is a much lower material emission than the other one by a substantial amount, but it's still equivalent to over 70 years of operating emissions. So again, you know, even when we get into a more sort of moderate material palette, the materials are still the dominant part of the emissions profile. well past when we have to care about things for the climate. 70 years is not the time when we want to start seeing paybacks on carbon footprint. So the moderate version still leaves a lot to be desired in terms of meeting climate goals. So the third model starts to look different and quite positive. This is the first model in the study that has a net carbon storage. And this was achieved pretty simply. The main things that we changed in this model were the cavity and the roof insulation were cellulose, the exterior continuous insulation was wood fiberboard, and the concrete was the best mix that we could specify for the Toronto region for this project. Pretty much that's the deal that pushes this model from having a pretty substantial carbon footprint to being a net carbon storer. And so you can see what happens if we start the building in a position of net carbon storage with a minus number. It operates for 20 years and it's still a net storer of carbon. And so I think that was the reason we titled the report achieving real net zero carbon buildings. It's because it's only a net zero carbon building if when you add both of these things up together, the materials and the operation, it's at zero. So if we can get there, then that's where we need to be. And this is a pretty achievable model of a residential building to be able to get there. So that's going to extend out for 45 years. So this building won't have a net carbon footprint for the next 45 years, which is pretty much what we need to do. And it's pretty great to see that it is doable. Again, this model had all materials that you can go get your hands on and use pretty easily today. And then this is sort of the more ambitious model. This is using materials that maybe aren't so common. We know that they're doable because that's what I do in my day job, is make buildings like this. But so this has things like straw bale walls instead of cellulose walls. It has pressure treated wood foundation. It has things like linoleum and cork flooring in it. We sort of threw as much carbon storing material as we could at this building. And you can see what happens here is, the amount of carbon storage is actually really substantial. A building like this actually starts to be a noticeable kind of reverser of climate change and not just a zero. And so this building is going to stay net carbon storing for almost 200 years. So well past my life, my daughter's life, and whatever children she has, their life, and maybe beyond that too. So, I think if we want to be building in a way that we can really look to future generations and say, yep, we did what we could to help you have a climate that you can live with. This is where we need to be aiming our practice. So this is just those models, put together so you can kind of see the extent. Essentially we built the exact same home. It's got the same number of rooms, the same level of energy efficiency, the same number of doors and windows, functionally and operationally the same building, but its carbon footprint is, can fit anywhere in this really, really wide range. And so, I think there's a way to sort of look at this literally as a series of steps. Like if I'm here, then I need to get here and then here and then here and then here and then here. We don't have to just all get to the green right away. There's a way to sort of progress ourselves there that, each one of these steps is really substantial. Like this blue model is less than half the carbon footprint of the red, and the yellow is more than less than half of the green, et cetera. These are big steps. We could break them up into smaller steps as well. So I think, figuring out where you are on that progression and then figuring out, just how to get yourself to the next step first, and then the next step is a pretty good way to look at that. So I'm going to switch up a little bit and just talk about that carbon storage in buildings, because that sometimes it took me a while to wrap my head around that, and I know that happens a lot for people kind of hearing this for the first time. So the way all of the materials that in this study that had carbon storage are plant-based materials. There also can be carbon storage in minerals, but none of that technology is really at hand right now. Hopefully it will become soon. Things like concrete aggregate gravel made from CO2 that's pulled out of the smokestacks of cement factories. Things like that are happening now and starting to be scaled up. But right now, if we want to put captured carbon dioxide in buildings, it's going to be plant-based. So plants absorb CO2 as they grow. That's what they do. The C stays in the plant. The carbon, becomes part of the body of the plant, and the oxygen comes back out for us to breathe, which is a really great byproduct. And literally billions and billions of tons of carbon come out of the atmosphere every year this way. Just grain straw alone is 4 billion tons of captured carbon dioxide annually. That's the emissions of India, the third or fourth biggest emitter on the planet, is completely taken out of the atmosphere just by grain straw every year. But then we burn that grain straw, or we let it rot, or in some way that carbon goes back to the atmosphere and we lose it again. So the CO2 is sort of pulled down by the plants, and we kind of interrupt it by putting it in a building for some chunk of time, hopefully a decent length of time, like 60 to 200 years. And maybe then it will come out, but maybe then we'll have the climate under control. We won't be burning fossil fuels like crazy, or we'll be smart about carbon and people will do appropriate things with it when it does come out. But the idea is we're sort of interrupting that carbon flow. We're taking carbon that would have gone back to the atmosphere and sticking it in buildings for a long time so that it doesn't end up back there. And you may be wondering, that was a weird building choice, Chris Magwood. Why did you put a picture of that building here to talk about carbon storage? And I picked that one especially because it's a very large straw bale building. It's a 7-story apartment building in France, mass timber frame, prefab straw bale wall panel enclosure around the outside, probably the biggest carbon storing building on the planet. Pretty cool. We can do this right now today. This thing has a monstrous amount of carbon storage in it. And it's things like this that we're going to have to do if we really want to drive towards that sort of best case green building model. Some places that we've done that store carbon, there's a little straw bale residence. There's a hempcrete and hemp bat insulation institutional building at Trent University. There's a very large straw bale school also in France. So, we're not pipe dreaming here that this is possible. And I'm sort of using some straw examples here because that's the world I'm from, but people are doing this with bamboo, people are doing it with rice hulls, people are doing it with agricultural residues of all kinds. So these are the kinds of buildings that sort of would exemplify that green typology of net carbon storage. Because you're a technical bunch, I thought I would sort of get into the technicalities of carbon storage. This has been an interesting ride for me. I'm not a climate scientist. I'm not really a scientist of any kind. I'm a builder. So wrapping my head, I could get that, okay, carbon comes from the atmosphere, goes in the plant, stays in the building. Okay, great. But what does that actually mean for the climate? Luckily, climate scientists have thought about this and they know this and they figured this out. So what this is showing is the yellow part of this graph is starting with 1 ton of carbon emissions. So if today one of us emitted a ton of carbon, we drove our car for a few miles, poof, there's a ton of CO2 in the atmosphere. That stays in the atmosphere. It decays slowly over time. This ends at 100 years. It continues to have an effect on the climate beyond 100 years. But over 100 years, that pulse of carbon dioxide is said to do 46 ton years of damage to the climate. I don't actually know what a ton year of damage to the climate looks like, but that's sort of how it's mathematically created. So on the flip side down here is a ton of carbon that we store. So in our building, in the cellulose insulation of your building, you put a ton of carbon. If that carbon stays in that building for 46 years, it has done the opposite of 46 ton years of damage. It's relieved the atmosphere of 46 ton years of damage. So in other words, when the green square has the same area as the yellow area, then we've offset, fully offset a ton of carbon. So, you know, anything that we're going to put in a building that's going to last 40 to 50 years. So things like the insulation, things like the framing, things, you know, the sort of main parts of the building that we're not going to change out, then that's how we can sort of, there's sort of a climate science justification for that being a meaningful amount of carbon storage. So what that means, everybody's always like, yeah, but when the carbon comes out of the building, doesn't it just go back to the atmosphere? Yes, it does. But in the 50 years that it's been in the building, it has done the work of taking a ton of carbon out of the atmosphere. So at that point, it's basically like it's a new emission. And obviously we don't want, you know, to burden future generations with lots of new emissions. But at a time right now when we're still burning fossil fuels uncontrollably, like giving ourselves this 50, 80, whatever it is, 100-year window of removing carbon from the atmosphere is, you know, one of the few options that we have to kind of stop the runaway freight train. If we figure out how to stop that runaway freight train, we'll probably have figured out better things to do with carbon when they come out of buildings than burning it. But, you know, this is sort of, when I talk about carbon storage in buildings, that's what I mean. The stuff that's going to hang out in a building for, you know, 46 seems to be the magic number, but you can call it 40 or 50 or somewhere in that range years. And then we can also then use ton year accounting to sort of weight the value of that carbon storage if it's there for less or more time than 40 years. So, you know, if I put 100 tons in a building and it's only there for 1 year, then its offset value is 1/46 of its weight in carbon. If it's there for 20 years, it's almost half the amount. If it's there for the 46 years, my 100 tons in the building literally has offset 100 tons. If it's there for longer, it's actually offset more than 100 tons. It's done, you know, more work because it's been out of the atmosphere longer. So, you know, built into the sort of the tool that we've built is that logic. If you know, a product has a 30-year lifespan, then I'm using the 30-year storage value. If it's got a 50-year, I'm using the 50-year. So we can sort of fine tune the meaning of that carbon storage using that ton year accounting. So I'm working right now with my colleagues on a study for the Toronto region. With Passive Buildings Canada and sponsored by or funded by the Atmospheric Fund, we're actually doing case studies of 100 recently built homes in the Toronto region. It's the first time that somebody's like benchmarked that many homes. And I just wanted to give you a sense, we're not quite done yet, but here on the left are the results from that Enercan study. So our worst case model was just under 140 tons for a 2-story building in Toronto. Our mid-range was 30, and our sort of best available materials was -20. When we actually are doing as-built homes, here's what we found. 88 tons is the worst for a 2-story home. So the worst isn't as bad as our worst case scenario, but the very best home in that whole study, or 2-story home anyway, is 50 tons, which is a whole lot worse than our sort of mid-range estimate over here. So, you know, as we look at real buildings, we're finding that they're all kind of landing in between the red and the blue sort of model in sort of real life. And so, you know, it's not the absolute worst case scenario, but it's far, far, far from the best case scenario. And we'll have that study out first thing in the new year. So I'll make sure that I send it everybody's way so that it gets seen. We also just finished for the cities of Nelson and Castlegar in BC. We did 35 homes there. So again, these are actual as-built examples. And there we found that the average house was 26 tons, and again, bracketed quite widely by 63 as the highest result and 5.9 as the best result. So, you know, the average looks good compared to the other study, but again, like there's this wide range that they fall in, and so super important to know that like in the same region within the same couple of years, people buying materials from the same store can turn out a 63-ton house or a 6-ton house, and it had nothing to do with its level of energy efficiency, or it's really comes down to material selection. And the average operational emissions from those homes were 1.25 tons per house. So again, we sort of see a wide bracket well under a ton. At 0.14 was the best result, and almost 5 was the worst result. So same kind of thing, like the possible range is really wide. But if we take the average, again, we see that thing that keeps happening of it takes at least 20 years of operations, if we use the average from this study, before operations have caught up to materials. And from that Nelson study, this is what the sort of material categories broke down. So when we amalgamated all the results and all the materials out of that study of 35 buildings, concrete was responsible for the biggest chunk of emissions. So across the whole study, just over 34% of all the emissions were concrete. Insulation came next at 18.8%, cladding at 13.2%, windows and interior surfaces being flooring, wallboard, and ceilings are pretty similar at around 10. Framing is also around 10. Roofing pretty small at 2. And structural elements like posts and beams and things like that, pretty insignificant. And down here at the bottom is the cellulose was the only carbon storing insulation in that study, but there was in total 41 tons of CO2 stored in the cellulose across the study. So that's kind of what it broke down in Nelson, and it's pretty similar to how it looks like it's breaking down in Toronto and likely, pretty much across North America. The one that changes a lot can be cladding. Places that use a lot of brick, that tends to be higher. Places that use sort of more wood and vinyl tends to be lower, but this kind of breakdown is pretty typical. One thing we did for the builders in Nelson was we took the house that had the worst results, and we sort of looked for the low-hanging fruit where we could make a really big difference in the carbon footprint with just a small number of changes. So we took the average concrete from that building and subbed out the results for a high SCM concrete, so something with a lot of slag or fly ash in it, and also like a Portland limestone cement. We changed the foam ICFs for wood chip ICFs. We changed the mineral wool wall insulation for cellulose. We changed the XPS continuous that building had for wood fiberboard on the outside. We changed, it had hardwood floors throughout. We changed half of those to linoleum, and we put cellulose in the roof instead of mineral wool, and we halved the carbon footprint of that building. So 6 relatively straightforward steps, nothing that is too difficult to achieve. In a lot of cases, not necessarily even any more expensive to achieve, and we can cut the carbon footprint of that building in half. We haven't addressed the design of the building or anything, just its these 6 material interventions. And then we decided to pick 6 where we could take it a little further. So we changed the EPS that it had under its slab for foam glass gravel. Again, we switched out the concrete. We changed the ICFs to a treated wood foundation, changed the walls to straw bale, changed the floors to a mix of linoleum and cork, and we put cellulose in the roof again. And that brought that 300 kilogram per square meter house down to just 55. So again, a handful of material swaps. The ones on the right may not be ones you're going to jump to immediately. They may not be things that you're considering, but all achievable, all things that people have done and a pretty dramatic tenth of the carbon footprint of the original house. And then in that Nelson study, this house came to our attention after we had run the study, but the energy advisor who was helping us out there said, hey, I think I've got a pretty interesting little building. I ran it through the calculator just because I was curious, and it has 2 kilograms of CO2 per meter squared. So essentially a zero carbon house on the material side. And the biggest things that contributed to that were it had no concrete in the foundation. It's up on helical piers. That allowed it to have cellulose in the floor instead of any kind of foam in the slab. Cellulose wall insulation, wood cladding, and cellulose roof insulation. Not terribly radical as far as the building goes, but a radical change from sort of the average of that study in the 150 range down to basically a zero carbon building. And it was great, in that study to be able to talk to the builders and other folks in those 2 municipalities and say, like, this is actually going on, in your jurisdiction right now. You could be building this, everybody could be building this. You don't have to necessarily build it this way with these materials, but these kinds of results in terms of carbon footprint are achievable. It's not a pipe dream or anything. So I wanted to dive a little bit into the concrete because it does end up in most residential buildings being a pretty significant portion of the carbon footprint. Obviously, there's things you can do like not use it or reduce how much you're using it. So by sheer volume, you can make a difference. But also, asking your suppliers for just to know what the carbon footprint of your concrete is really helpful. And B, pushing them to start offering lower carbon mixes. So when I look at the concrete EPDs that are available across North America, I can see that there's a best achievable of only 136 kilograms of emissions per cubic meter of concrete. And I can see that about 20% of the EPDs are above 650 kilograms per cubic meter. That's a big split. Like, when you get to site and it's coming out of the spout, it just looks like concrete. There's no performance difference. This is for the same PSI. It's for the same like basic residential mix that anybody would use, but there's this giant gap. For our studies, we're using this Canadian average of 369 kilograms per cubic meter. But, by and large, we don't even know what people are using because most ready mix plants that are supplying residential buildings aren't producing EPDs. So, one of the things you can do is start asking your concrete supplier for, hey, can you make me an EPD for this mix that I'm getting? And if the numbers look terrible, like this one, 650, ask them to do better or take your business elsewhere if you can, because there's lots of things that they can do to bring that down. And just, the difference here is if we use the best number, the same wall, like 1,000 square feet of 8-inch wall could have, 2.5 tons of emissions or over 12 tons of emissions. So it's a 10-ton difference. It's still a concrete wall. It's like if you looked at it, if you built a house on it, you would not know there's any difference, but the climate feels that kind of, 10 tons per house difference. So, everything we can do to make sure that we're bending that down is really great. For Nelson, we sort of did this little wall systems comparison. We just looked at some of the ones that were quite common across the houses we studied there. And you can see, basically we tried to normalize this so that all of these are achieving an R24 level of performance. And, you can get anything from, 9 tons of emissions from the worst case to 5 tons of storage in the best case, and kind of everything in between. So thinking about, how we pick those materials, what goes into the assembly is really important. I know there's a lot of people, I get like more email about this than anything else. Yeah, there's this new XPS formula coming out. It's a real game changer. It's kind of a game changer. It changes XPS from being like shockingly by far the worst insulation to being kind of just the worst by a little bit. So, it's not It's not going to change the world, but it is a pretty significant improvement, and it makes it, about the same as doing mineral wool cavity and mineral wool board on the outside. Glad that that's happening, but it's not sort of the silver bullet that it's sometimes being made out to be. This was interesting. I hadn't really thought about this because in my practice, I don't really build houses for cars, but a lot of people do. So 19 of the 35 homes in Nelson had garages, and they had 122 tons of emissions just from the materials that go into the garage. So basically 20% of the emissions from houses that had garages were attributable to the garage. So if you want to cut the carbon footprint of your building down, don't make a building for a car. You can knock a fifth off your total right there. Don't do anything else. Just don't make a house for a car. So I'll kind of go through this quickly. These are the takeaway points for the group in Nelson. I really want to make sure that people look at the first two here. Even though I'm saying that material emissions are a lot bigger than operating emissions, I am not at all suggesting that we give up on operational emissions and only think about materials. Like, I really think these two things need to go hand in hand. The kind of results where you actually get a real zero carbon building, it really has to be net zero on the operational side, and it needs to be zero on the material side. You can't really just put all your attention in one place or the other. We really have to be doing these things hand in hand, and really, thinking about them holistically that way. So I think I'm done in a reasonable amount of time for leaving lots of time for questions. I can't see the chat, but I can see there's like 87 things in there. So I'm assuming that there are some questions. So we can start doing that.
Yes,
now.
Chris, there is a lot. I think I got about 12 people on the queue for that. But Kevin or Mark, any points you want to dive into before we take on a question?
I think it was a great presentation, and definitely going to make me think a little bit more about the materials we choose. I know I'm going to be putting pressure on getting better concrete in our projects, and I've always been excited about using some foam glass as a with the new site up in Vermont. It's exciting that hopefully the foam glass gravel gets more into our market. And as a cellulose contractor, it's what I grew up doing as a weatherization installer, and I still believe in it. And now having the data behind to show people that cellulose is a carbon sequestering product, I'm going to push it a little further. Thanks.
That was a fantastic presentation, Chris. Thank you so much for that data. My eyes are opened once again. So I really like the slides that you used to ask, what changes can I make to reduce MCE? So I think you've got a whole bunch of people that are going to seek out and adopt new products and push their suppliers for more effective solutions. And I want to jump off early tonight, but I'll miss hanging out with you guys in the after hour. So thank you, Chris. And I'm throwing into the chat the link to that NRCan report. So everybody make sure you click on that link and download that report and give it another look.
Hopefully you got a second to fill out the survey so we get an idea of who's here. That would be great. Mark?
I'm going to save my comments until we come back, Sean. I'm going to say goodnight to Shannon. We'll see you next week. First and foremost, thank you to Chris, and pass the mic to Zach.
Great. I really want to just defer to everybody else. Chris, this is an amazing presentation, and your work is always so provocative and is playing such an important role in the community. So I think that, I'll go to one. I'll just ask one question. I had four, but just one, and that is, I've heard considerable skepticism about the potential of wood in buildings to actually sequester carbons. There's no question that we can do less harm with wood in buildings, but there's some skepticism around wood being a real sequesterer at scale, partly due to how much bad forestry is going on, and also the argument that the accounting for what's going on in the soils with wood harvesting is not necessarily a part of the carbon accounting. So I'm curious to hear what your sense is of the the actual like carbon sequestering potential of wood, and then how that I guess the following question is it really the quicker the faster cycle plants like straw that we should be looking at for their potential to sequester?
So I'll answer your second question first with yes. The carbon accounting for short cycle plants, in particular, things that are either like from our waste stream, like cellulose, or things that are agricultural residues, the carbon accounting on those is really simple. That material was already being produced, or grown, not to be a building material, but to eat, or, the cellulose used to be a newspaper or a cardboard box or whatever. And we know for sure that carbon was going back to the atmosphere really soon. So, in the case of agricultural residues, we also know that we're going to draw that same amount of carbon down next year and be able to put that into a building, and next year and next year and next year. So that's pretty straightforward carbon accounting. I think I actually didn't make it clear that no wood products were given any storage value in any of these studies. So we were only valuing waste stream and ag residues and things like that, just for all the reasons you said. I mean, there is an awful lot of question as to whether carbon storage in wood is doing good for the climate. I think it's pretty clear that using wood is better than using steel or concrete. I think that case is compelling, but whether or not we're doing something actually positive for the climate by sticking wood in buildings, the jury is still very much out on that. And I think the final answer is going to be, it depends. And the depends will be what's going on in the forest where that wood came from. We have to, if we're going to take carbon out of a forest, which is like a growing ecosystem and a place where a lot of carbon gets stored in wood, in the soil, even in dead wood while it's sitting on the ground, and all the ecosystem services that are going on there, they're important places for the climate. If we can grow the carbon stock in a forest while taking wood out of the forest and sticking it in buildings, that's meaningful carbon storage. If we're just taking carbon from over here and sticking it over there and maybe leaving less carbon in the forest as we do that, that's bad for the climate. And I think, right now, the only EPD for wood in North America is like an average that by the Canadian and American wood councils that averages like a whole bunch of mills. And we sort of have this one number that doesn't speak at all to what's going on in this forest. It's different than that forest. It matters whether, they cut their trees at 40 years or 50 years. It matters that it's further north. And so it takes the trees 20 years longer to grow. That, there are so many factors that I think we need to get to a point where, I can look at an EPD for a specific forest or from a specific mill, and it reflects the forest practices of that particular spot. And I can say, that's good wood and this is not good wood, and be able to make choices there and actually show the carbon storage where there is a valid case for storage, and show it as an emission where it's valid that it's an emission. So for now, our tool just counts the emissions from the wood EPD, but it doesn't count any storage in wood. And I probably should have made that clear, as I was talking about it, but thanks for bringing that up. It's really important.
Oh, no. Yeah, absolutely. Thanks, Chris. I think that, and great, very helpful answer. And I think it's just a question that we in the community are grappling with, because if you get to a place where you decide that something is actively good for the climate, then you want to do more of it. You want to use more of it. And so that's the interesting question around even sustainably produced wood. We want all wood in construction to be used sustainably, or to be wood that is sustainably produced. But there's a big difference between that and deciding that we need to use also use more sustainably produced wood everywhere. You know what I mean? It's a distinction that I think is important for us to wrap our brains around. So thanks, appreciate it.
Yeah,
Zach,
yeah, no problem. And it is one of those things too, where, you know, it's all of those decisions take decades to figure out. It's going to take us probably a decade to figure out what good carbon storage forestry practices are. It's also going to take a decade for things like mass timber to scale up to the point where if it is good, we can start doing it at scale. It's good, you know, like, and I think, you know, I think it's great that we are pursuing mass timber, because I think we're not doing it at a scale right now that is going to tip the climate one way or the other. But if it turns out we can do it and it's good, it's great that architects know how to design them, builders know how to build them, all of that kind of stuff. So I think, yeah, we're in a funny place now where it's like, yes, you want to see this happen. You really want that work to go on, but you don't want to be like just a cheerleader because we don't actually know yet. So it's kind of like we should all be figuring it out and like ready to go if it turns out that it's the right thing to do, but also ready to go, nope, maybe we shouldn't be doing so much of this. And yeah.
Fantastic. All right, Zach, you can switch from being a question provider to giving us the sponsors and the updates.
Oh my gosh. Okay. Sorry, everybody. I'm not supposed to do it this way. Okay, here we go. I'll go quick. All right. So everything we do at the Accelerator comes thanks to the support of our sponsors. So thank you to our founding sponsors, 475 High Performance Building Supply, Baxter Inkwee Architects, Glavel Foam Glass Gravel, Minotaur All-in-One HVAC and Dehumidification Units, Mitsubishi Electric Train HVAC US, Partel, RDH Building Science, Rockwool North America, Stillcorp, and Zola Windows. Our champion sponsors are Icon Windows and Doors and SIGA, and our stakeholder partner is NYSERDA, the New York State Energy Research and Development Authority. Thanks also to our patron sponsors, Aero Barrier, BR+A Consulting Engineers, Brennan Air Tightness and Insulation, Euroline Windows, Innotech Windows and Doors, Lamelux, Sanderson Sustainable Design, and US Engineered Wood T-Stud. So we have Dr. Diana Urga-Vorsatz of the IPCC, the Intergovernmental Panel on Climate Change, on the podcast this week. It's a really fantastic interview with Matthew Cutler-Welsh, where Dr. Urga-Vorsatz shares her thoughts about the urgency of the climate crisis and the window of opportunity we have to address it, and how important buildings are in climate solution making. So I really urge everybody to listen to this. It's great timing moving to the COP26 conference in Glasgow next week. We also have a special Passive House component episode of the podcast with Hugh Borowski of Partel, where he talks about his journey from being a practitioner and engineer to being a producer and leader in high performance building materials. So check that out as well. So, and then tomorrow we have a really inspiring presentation by Green Hammer, the design build firm based in Portland, Oregon. They go into the details of the New Day School, which is a net zero energy project that draws on very heavily on passive house design principles and approaches to achieve its very low operational carbon, and also it has a focus on low embodied carbon. So a nice follow on to this. It's both and message that we're hearing tonight. Then on Thursday, we have our first ever Building Performance Interactive, episode 1. This is a UK and Ireland-based mini-series that will unfold over 8 months. The first episode is this Thursday at 2 o'clock in British Summer Time, which is 9 a.m. Eastern Time and 6 a.m. Pacific, and it will feature Tomas O'Leary as the special guest, and I can't wait for this first episode on Thursday. Next Tuesday, we have construction tech. We have the return of Holstrom Systems with Sim Part 2, and you'll want to come back for more amazing modeling and integration information on Tuesday. And then Thursday, we have another kind of innovative construction techniques presentation from Bonnie Doon, B Public Prefab. This is thoughtful rebuilding after a devastating fire season, looks at a Santa Cruz Mountains rebuild that took 6 months from design to construction of the structural and thermal envelope. Really phenomenal and great story. Can't wait for that one as well. Finally, on Friday of next week, so November 5th, we're going to be kicking off the Passive House, the International Passive House Days, with a live virtual tour of the Engine 16 Passive House retrofit with Michael Ingui, who we heard from earlier about Source 2050, Amy Fayet, also at Baxter Ingui Architects, and Ken Levinson of the Passive House Network. So join us then for that as well. I'll include some links in the chat. Okay, bye.